So today we're going to continue our study of virtual memory by looking at in more detail at how address translation works, and then we'll learn about how virtual memory works on real systems, on Linux and x86 64 systems. And the payoff for that is that you'll really be able to now understand how fork and exec really work and how vital the virtual memory system is to the sort of the entire working of the system. So let's look at some specific examples of how we do address translation. And here's that reference slide. So let's suppose we have this simple memory system with 14-bit virtual addresses, 12-bit physical addresses, page size of 64 bytes. So we need 6 VPO bits, offset bits, and then the remaining bits are the virtual page number. And similarly for our physical addresses, we need 6 offset bits, and the remaining bits form the physical page number. Okay, now the TLB in this system has 16 entries, and it's 4-way set associative. So you remember that the TLB caches page table entries, okay, and those page table entries are uniquely identified by the virtual page number. So we only need to use the VPN to access entries in the TLB. We have 16 entries, 4-way set associative, so there's a total of 4 sets. And so we use the the 2 low order bits in the VPN as the index, and then the remaining bits, just like any other cache, are the tag bits. Okay, and then we've initialized this with some various values. Now notice that the actual contents of the TLB are in this region here, right? So the set, this is just to help identify what's set. There is no entry called set with a value of 0, right? We're just identifying that we're just explicitly listing the index. And so each of our entries in the TLB consists of this tag. And if the TLB entry is valid, a physical page number. Okay. Now, we also need a page table, so we'll assume that we have this page table with, we're just showing the first 16 entries. And each page table entry consists of a physical page number and a valid bit. If valid bit is on, then that indicates that the page is in memory, and the PPN field gives the physical page number. Okay, and again, there's no actual, this VPN column doesn't actually exist in the page table. Okay, and now we have a simple direct mapped cache. It's addressed with physical addresses, and it contains 16 sets, each with 1 line, and we'll assume a 4-byte block size. So we have a 4-byte block size, so we need 2 offset bits for the cache. 16 sets means we need 4 cache index bits, and then the remaining bits are for the tags. Now, it's just an accident in the way that I define this system that the cache tags are exactly the same as the physical page number. So this is just a coincidence. It isn't necessarily that way. Okay. Now with the magic of AV audiovisual systems, switch. Good. Okay, so we're going to look at a couple examples using this little system. Okay, now so let's suppose the CPU executes an instruction that generates an effective address, it's a virtual address, of 0x03D4. And then it passes that to the MMU, which needs to figure out the corresponding physical address, and then it needs to fetch the data from cache or memory. Okay, so the first thing we do is we just write out the bits for this virtual address. Okay, and then we identify the different fields. Okay, so we have the offset, virtual page offset bits, and then the remaining bits are the virtual page number. Okay, the offset in this case is 24, 0x24. The VPN is F. And then we have the two TLBI bits, which are 1, 1, so 3. And then we have the tag bits, which are also equal to 3. So the first thing that the MMU does, given this address, is it checks the TLB on hoping that the page table entry that it needs is cached in the TLB. So it goes, extracts the index bits, 3, and that gives us, so now that says that if this page table entry is in the TLB, it's going to be in set 3. Okay, so we go to set 3, and now we're looking for an entry in set 3 with a tag of 3. Okay, so we go across this one. There's 4 entries in this. Here's an entry with a tag of 7, so that's not it, and plus the valid bit's 0. Here's an entry with a tag of 3 and a valid bit of 1. So we lucked out. The page table entry's in the TLB, and so the TLB returns the value, the physical page number, which is 0D, back to the MMU, which can now construct the physical address. So it constructs that physical address, PA, by directly copying the VPO bits to the PPO bits. Okay, right, as we discussed the last time, the virtual page offset's always identical to the physical page offset because the block sizes in the virtual address space and the physical address space are the same size. Okay, so we get the low order PPO bits, and then the physical page number, which comes from the PTE that's cached in the TLB, is 0xD, and so that forms the PPN bits of the physical address. So these now constitute our physical address. So now the next step, once we have the physical address, is to send that to the cache and ask the cache to return the value at that address. Okay. And in this case, we're just doing 1 byte accesses. Okay. So we're asking the cache to return the byte that's at this physical address. Okay, so the cache, of course, it first checks to see if the byte that's requested is contained in some block in the cache. Okay, so it takes and it extracts the cache index bits, okay, which is 0, 0, 1, 0, 1, so 5. And so if this byte that's being requested is in the cache, it's going to be in set 5. So we go to set 5. And then we're looking for a tag of 0xD. And lo and behold, we have a matching tag and a matching valid bit. So the line that we requested is in the cache. And the word that we requested is at offset 2. Okay, so we go to, so this is offset 1. This is offset 2. Oh no, I'm sorry. Let's see. Oh, I'm sorry. It's at I was getting confused. These are the index bits. So the offset is actually 0. Right. And here's this is our physical address. Okay. And the value of that offset is 0. So we're asking for in the fifth set, we're asking for the byte at offset 0, and that's 0x36. So we have a hit. The cache returns that byte back to the MMU, which passes it back to the processor, which stores it in a register, most likely. Okay, so let's look at another example. And I've recorded these here for you if you want to go back and look at them. Let's look at another example. So this time the CPU sends a virtual address of 0x0020 to the MMU. Okay, and so if we write out the bits for that virtual address, we get this result, and then we mark off the virtual page offset, the virtual page number, and the TLB index, low order bits of the virtual page number, and then the tag for the TLBT. So as step 1, same as before, check with the TLB. Let's see if that page table entry is in the TLBT, in the TLB. So we're asking, in this case, this set, if this page table entry is in the TLB, it'll be in set 0, okay, and it'll have a tag of 0. So we look in set 0 for a tag of 0. This doesn't match 03. Here's 09. That doesn't match. 00 matches, but the valid bit's 0. So this isn't a valid entry. It's just a coincidence that this tag was 0. So this is a TLB miss. Okay, so that's a bummer because now we have to go off the chip and make an expensive memory access to read that page table entry from the page table. So now we have to check with the page table. And we're looking for virtual page 0. So we check the entry at virtual page 0 to see if that page is in memory, and if so, if it has a valid, if it is in memory because the valid bit's 1, so we have a valid physical page number. So the memory returns the page table entry, or the PPN back to the MMU, which is it's a 0x28, and now the MMU can use that physical page number to construct the physical address. So as before, we copy the virtual page offset directly into the physical page offset. And then our PPN is 28, so we have 10, it's 2, 10008. So now concatenated, those form the physical address. And now the MMU has a physical address that it can hand off to the cache and request that the cache return that value at that physical address. So now the cache gets that physical address, and it extracts the cache index bits, which in this case are 8, okay, 0x8. So if the word that we're looking for is contained in the cache, I'm sorry, if the byte that we're looking for is contained in the cache, it'll be in set 8. Okay, so the cache goes to set 8, and it looks for a matching tag, which in this case is, it turns out that it's 28, just like the PPN, just by coincidence. So in set 8, we have a tag of, we have an entry, the block has a tag of 24, so there's a miss. Okay. So this is a cache miss. So now the cache has to request pass that physical address to the memory to fetch that byte. Yes?
I just have a quick question. How do you know the size of the virtual page offset? Is that based on the page size?
How do you, yeah, the question is, how do you determine the size of the virtual page offset? And yes, it's based on the page size.
Okay. So what are we assuming the page size is then?
It was 64 bytes. Okay. So 64 bytes, so that's why we have six VPO and PPO bits. Okay, so is that clear to everybody? That's the kind of thing that sometimes turns up on exams, you know, just. Yes?
Is there any relationship between the length of physical page number and the cache tag on the server?
Okay, so the question is there any relationship between the length of the physical page number and the cache tag? This was just a complete coincidence. Okay, it just happened. It was just a coincidence. They don't necessarily have to line up like that. Any other questions? Yes?
So you said in this case the fact that the PDN is also 20 was a coincidence?
Yes. For instance, if I'd had more sets in my cache, then I'd need more bits and they'd spill over, right? It was just a coincidence because I had 6 PPO bits and just a block size of 4 and 4 sets. So if my cache had more sets, the cache index would spill over and then the cache tag wouldn't match up with the physical page number. Okay?
So it's a similar situation to the question before where, like, in this case, it's just coincidence?
That's right. It's similar to the question before. It just happened to be a coincidence. Maybe I should have chosen a different example, but they're completely independent. Everybody else good? Okay. Okay, so now I want to talk to you about how this stuff all works in a real system. In this case, it's a Core i7 system from Intel. It's an x86-64. It's a family of high-end desktop systems, x86-64, similar to the Shark machines that you use to do your labs. So here's the way the memory system looks in the Core i7. The processor package is the chip. Okay, so that's like a single. And then there's 4 cores in this package. Each core is a separate has a separate CPU and can execute instructions separately. Okay, so each of these cores has a register file. And then some hardware that fetches instructions. It has 2 L1 caches. There's a data cache called a D cache, which is used to fetch data, and which holds data fetched from memory. And then there's an instruction cache called an I cache, which holds instructions fetched from the code region. So the D cache has data only, the I cache has instructions only. They're each 32K bytes, 8-way set associative. So they're very small, but they have fairly high associativity. And then the next level in the hierarchy is an L2 so-called unified cache, because it can hold both instructions and data. Okay. It's a little bit bigger, 256K bytes, and also 8-way associative. And so both of these caches are on the core itself. Okay. And then there's an L3 cache, which is shared by all cores, which is 8 megabytes and 16-way associative. Okay, so the access is, because the L1 cache is closest to the processor, this is fast. This is like 4 cycles to access L1. L2 is bigger, and a little further away, so it's about 10 cycles to access this. And L3 is off the core, right? So it has to go over a connection, some connection off the chip into this cache. And so the access time for this L3 cache is like 30 to 50 cycles. Now the MMU has it also has a hierarchy of TLBs, and I was talking with a student after class the last lecture, and I mistakenly said that the system didn't have a hierarchy of TLBs, but it does. There's a small L1 data TLB and a separate instruction TLB. So this has 64 total entries, and it's 4-way set associative. So how many sets are there then in this? How many sets in the L1 data TLB? 16, right? Good. And then the instruction TLB has more entries, interestingly. So it's an interesting decision. I guess the thinking, I don't really know. I'm just conjecturing that the reason they would make the instruction TLB bigger is that the penalty for missing on instructions would be much larger. But yeah, I'm not sure. It's an interesting decision. And then there's a unified TLB below that, which is larger still. So I think if you're wondering, I mean, it's interesting to think, like, why do they have these, like these second level caches? Why didn't they just make these the L1 caches bigger, right? And in the case of the D cache and the I cache over here, I'll show you in just a little bit if you hang on. There's a really interesting reason why they can't make these things bigger or much bigger, right? There's a property of the they're constrained in the size of the offset and index bits in these caches. And it's interesting. I'll show you in a second. For the TLB, I mean, one reason that comes to mind for why they have this second level is that if they decided just to make the L1 DTLB and ITLBs bigger, take the transistors that they used for this L2 and just give them to the level 1 TLBs, you kind of by partitioning those that storage ahead of time, you're kind of locking yourself in. So if you didn't have this level 2 TLB and you just increased, say you gave half, and so it made L1 and the data TLB and instruction TLB twice as big, then you're sort of locking yourself in, right? If you run, you still might run out of instructions and have capacity misses in that L1 cache, and similarly for data, right? So you're not sure. You may, in a particular program, there may be a lot more data page table entries than instruction page table entries, or vice versa. So by creating this second level of cache, you're kind of hedging your bets, right? So the miss penalty, when you have this L2 cache, the miss penalty in L1 isn't nearly as big as it would be as if you didn't. Okay, so that's sort of the thinking that goes on. Now there's a memory controller which fetches data from memory, and then there's links to other cores and to the I/O bridge. Now end to end, so it's really interesting. So it's interesting to see how this all fits together end to end. So let's look at it. So the CPU generates a virtual address. In Intel systems, the virtual addresses are 48 bits. We have 4K size blocks, so 12 offset bits, and then 36 VPN bits. So first we look in the cache, in the TLB, and there's, as we said before, there's 16 TLB sets. This is the L1, I'm showing the L1 data TLB. So we break it up into 4 TLBI index bits and 32 tag bits. So we do a lookup in the TLB to see if we can find the PTE that contains the corresponding physical page number for this virtual address. If we have a hit, then the MMU can just construct the physical address directly by copying, as we saw before, copying the VPO to the PPO and then using the PPN that was returned from the TLB. How's that for an acronym? So, if there's a TLB miss, then the system has to fetch the corresponding PPN from the page table using that multi-way lookup multi-level lookup we looked at before. And I'll show you how this works in a little more detail coming up. But the end result is that a page table entry is located and the PPN is extracted from that and concatenated with the PPO to form the physical address. Then the MMU passes that physical address to the cache. The L1 data cache has 64 sets, so we need 6 cache index bits. Now, here's what I was alluding to before. Notice that the number of cache index and cache offset bits is exactly identical to the VPO in the virtual address. Okay, so the cache offset and index bits in the physical address are identical to the VPO, the offset bits in the virtual address. Okay, and this is not a coincidence. Okay, unlike that other example I showed you, this is not a coincidence, and this is at the root. This is at the root of why the L1 cache is so small. It's that the way Intel implements their cache lookups, which we'll see in a second, depends on the cache index and cache offset bits in the physical address being identical to the offset bits in the virtual address. So anyway, so then we do our cache lookup using the cache does a lookup using this physical address, takes the index bits to identify a set, uses the tag to see if there's a match. If there is, then we have a hit, which returns the resulting word back to the CPU. Otherwise, there's a miss, so then the cache has to request the data from L2, L3, and main memory. Eventually, worst case, that data comes from main memory. Well, I guess worst case, it comes from disk, right? If you have a page miss, a page fault. So eventually, though, the data comes back and is returned back to the CPU. Now, the page table entries in Intel systems have the following structure. You can see that the level 1 page, which levels the level 1 through 3 pages, remember that page table entry points to the address of the next level page table. Okay, so it contains the level 1. The level 1 PTE contains the base address, the physical address of the level 2 table, okay, and so on. There's a bit, this is the valid bit, they call it the P for present. So this identifies whether the page is in memory or not. If it's not, then there's the location of that page table on disk. There's bits that control whether that page table can be is it read only or it can be written? Oh, actually, this corresponds to all reachable pages. So, you can. So all reachable pages. So all of the portion of the address space that's covered by this particular page table entry. There's also a bit that indicates whether users can access that or if they need to be running in kernel mode. So this is how the kernel protects its code and data from user programs. There's a bit here to indicate whether we should be using write back or write through for this for these page tables, and all the systems I know of use write back just because of the miss penalty, the enormous miss penalty. I forget what CD does. There's a reference bit which is set when the MMU reads or writes that the page table that this points to, and then there's a bit that indicates whether the page size is either 4K bytes or 4 megabytes. Okay, and then there's this new disable. It's the XD bit which allows you to disable or enable execution from all the pages reachable from that page table entry. So this is how the stack, modern systems protect the stack from code injection attacks. Okay, the last level page table entry points to it points to not another page table, but actually a page in memory. Okay, and so we have the same bits here, the same 40 bits that give the physical address of that page in memory, and then we have the indication of whether that page is present in memory or not, and the read write and permission execute permission bits, write through or write back. There's this reference bit, and then there's a dirty bit which the MMU sets when it writes to that page. Okay, so this is how the OS knows that it needs to when it selects this. If it selects this page as a victim, it looks at the dirty bit to see if it needs to write that page back. Did you have a question?
What are the different kinds of protection that are being provided by the U/S bit versus the XD bit? You said they're both.
Execute means that you can't execute any instructions. You can't load any instructions from that page. Okay. This user supervisor mode determines whether you can access that page. So if it's set to supervisor mode, only the kernel can access that page, anything on that page. If it's set to U, then any user code and kernel code can access that page. Any other questions? Okay, so then the way it does address translation then is the physical, for this process, so the kernel for each process maintains the set of page tables, of course, and then it maintains the address of the first level 1 table in a register called CR3. Okay, and this is a physical address, points to the base of the level 1 page table. The VPN is broken up into 36 divided by 4 equals 9 bits that give offsets into each page table entry. Okay, so there's 2 to the 9th potential page table entries in each of these different page tables. So this VPN1 is used. The high order 9 bits are used to compute an offset into that table. And you can see each level 1 PTE covers a swath of memory that's 512 gigabytes in size. So you can see for most programs that exist today, you only need one level 1 page table entry to be initialized. That would cover the vast majority of your programs. The next 9 bits, so the page table entry in the level 1 page table points to it gives the physical address of the level 2 page table. And then the VPN bits in the virtual address are used to compute an offset into that table, and so on. It just cascades. And then finally, the low order bits of the 9 bits of the VPN are used to form an offset into the level 4 page table, in which each PTE points to an actual page. Okay, it gives a physical page number. So then that physical page number then is extracted and concatenated with the VPO, which we copied down, to form a physical address. Okay, so is that everybody good? Okay, now there's this cool trick which I was alluding to earlier that limits the size of L1 cache. Now to this point we've been using a model where the MMU takes does address translation and creates a complete virtual address, a physical address, and then it sends that physical address to the cache. Okay, but in reality, Intel does this cute trick to speed up L1 cache accesses. So in reality, what happens? So we're given a virtual address. Okay, and in this virtual address, the index and the index and offset bits in the physical address are identical, exactly correspond to the PPO in the physical address, which is exactly identical to the VPO in the virtual address. So what that means is that when the MMU is given a virtual address, it can send the VPO off to the L1 cache, even though L1 is physically addressed. We can send the VPO in the virtual address to the L1 cache because of this phenomenon that the PPO is identical to the VPO. So even before the MMU is doing any address translation, it can send these VPO bits to the cache, and then the cache can get busy extracting the cache index bits, looking up all of the lines in that set, and then have everything ready for the tag check, which can only occur after the address translation happens. So it can only occur once there's a physical address from which we can extract the cache tag. So there's a little bit of parallelism now in the L1 cache accesses. So the MMU can be doing address translation while the L1 cache gets going on its lookup. Okay, so now let's look at how Linux implements virtual memory. And in doing so, we'll now get a clear understanding of how fork and exec and loading really work. Okay, so we've seen this picture like this several times before. This is the virtual address space of a Linux process. Right? And because of the way the virtual memory system works, every process has a very similar looking address space. The program text, the code is always loaded at the same 0x400,000 address. Then that's followed by initialized data, which comes from the .data section of the executable binary. And then there's the BSS section, which contains uninitialized data that was defined in the binary. And then the heap grows up from the initialized data. It's pointed to by a global variable a variable in this process context called break. So the kernel keeps track of where the top of the heap is for this process. there's a memory mapped region for shared libraries. And then at the top of the user level, user accessible memory, there's this user stack which grows down and which is pointed to by RSP. And then the kernel code and data live up in the upper portion of the address space. Now, this picture isn't completely accurate. There's actually like a big gap between the top of the stack and the beginning of the kernel code and data. The reason for that is that the Intel architecture says that so there's 48 virtual address bits, right? So if the high order bit of that 48-bit address is 0, then all the remaining bits have to be 0. The remainder of the 64 high order bits need to be 0. So it's kind of like sign extension, right? And if that high order bit in the 48-bit address is 1, then you extend the 1 all the way up to the remaining high order bits. Okay, so those are the only feasible bits. So what that does is it creates the kernel's living in a portion of the virtual address space where the 12 high order bits are all 1s. Okay, so that creates, so you can think of it, the kernel lives in the very top of the 64-bit address space. Okay. Another way to think of it, kernel addresses always start with 1. The most significant bit is 1. And user addresses always have a most significant bit of 0. Okay, but that's just a detail. It doesn't really affect things. But what is important is that this is the process virtual address space of a process, right? And so the kernel exists in the virtual address space of each process, right? And so there's kernel code and data, and then it also maps. It has a region of its virtual address space that maps each element of this region with an address in physical memory. Okay, so this mapping, this region corresponds to the amount of DRAM on the chip. And so it's a mechanism that the kernel uses to get access to physical addresses. Okay, and this is important because, remember, the kernel, you can't turn off address translation, right? It's always happening. Okay, so even when the kernel runs, the address translation is happening. The kernel's generating virtual addresses. So this region, this is mapped to a region of physical memory, so that if the kernel accesses byte 0 of this block, it'll actually be the address, the corresponding physical address will be 0. And if it accesses a byte at an offset of 1 in this region, the physical address, the corresponding physical address from the address translation process will be 1. Okay. So basically, by reading and writing into this region, the kernel is reading and writing into physical memory. So there's portions of the kernel that are identical for every process, right? The code's the same. It's not. But then there's process-specific data structures that the kernel maintains for each process that form the context for that process. So we refer to all these data structures as the context. Okay. And these, of course, these will be different for each process. Now, Linux organizes this virtual address region as a collection of what it calls areas. An area is like a segment. Think of it as just a chunk of, a contiguous chunk of related memory items. So there's an area for code, there's an area for data, shared libraries have areas, there's an area for the stack, and it contains, there's a structure for each process called the task struct, and this contains a pointer to the struct, which has a bunch of stuff in it, but it contains the address of the level 1 page table. Okay, so that's part of the context. When this process runs, when this process is scheduled, the kernel will take this entry, this PGD entry, and it'll copy it into CR3. Okay, so that's how it switches. Just by changing the CR3 register, the kernel changes the address space. Okay, so that's how, and once that CR3 value is changed, then the process no longer has access to the previous process's page tables, right? So, and then there's a pointer to a list of these so-called area structs. The area struct identifies the start and the beginning and end of the region. Any protections, like is this read-only region? For example, so the code section would be set as read-only, or is it read-write? And then there's some other flags, which we'll see, we'll see later. In particular, when we look at sharing and mapping, for our purposes, these flag bits tell us whether the page is shared with other processes or whether it's private to this process. So normally the default is that pages are all private, but you have the option, if you do a fair amount of work, you can get processes to share memory. Okay, so let's look at what happens when we have a page fault. So let's say, there's, the processor issues an instruction, the address translation process determines that the corresponding page isn't contained in memory, so it triggers a page fault. And so the fault handler, there's several things that might have happened. One, maybe we were reading memory. It faulted because that memory, that area doesn't even exist. So we haven't even created, the kernel hasn't even created, allocated that page in virtual memory yet. Okay, so that's an error. So that's accessing a non-existing page elicits a seg fault. So the kernel figures that out because it runs down this list of area structs, and it doesn't find this address anywhere within the ranges of those areas. So that's a seg fault caused by accessing a non-existing page. Another possibility is that the instruction is attempting to write into a read-only section segment of the virtual address space. Well, there's nothing in the page table. The MMU typically would check the permission bits in the page table entry and throw an exception if a write is trying to write to a read-only page. But in this case, there was no page table entry, right? That's why it triggered a page fault. So the MMU doesn't know that this is an illegal write. But the kernel can check the protection for this area, and if in the case of text, it'll be set to read-only. So that triggers a protection exception, which actually Linux reports as a seg fault. Okay. And then the other option is that maybe we're trying to read data from a valid area. So then the kernel faults the requested page in and returns the requested data back to the CPU. Okay, the last thing I want to look at today is a yes. Okay, S, sorry?
When are the values in the VM area struct populated? It's only the linker that needs the beginning and end, the boundaries of the like.
Yeah, so all of the segments are contained in the executable file. Okay, there's at the beginning of the ELF binary, there's a list of all the different segments. Okay, so when exec loads the binary, creates areas for each of those each of those segments. Okay. Good? Yes?
So how exactly are the structs like used? So is this like, it still first checks like it does the MMU and it gets the page. Is this like once it?
This is after the page fault.
Oh, so this is only we only use these structs if there's a page fault.
Yes. The MMU doesn't know about these. Okay, so yeah, the question was exactly how are these area structs used, and they're used in this context, in this example anyway. They're used during the page faults. Okay, and also just as an aside, I've shown these actually are implemented as lists, but in the real system they use some kind of tree, a red-black tree or something like that. Okay, so I want to talk the last thing we're going to look at today is this interesting idea called mapping, and it will help us understand a lot about what's going on in the system when it executes fork and exec. Okay, so VM areas are initialized by associating them with disk objects. Okay, and so this process. Using a process known as memory mapping. Right? So every area and thus every page within that area is associated with some portion of a file, and that's the initial contents of the pages in that area come from that file. Okay, so an area can be backed by what we call, or get its initial values from either a regular file on disk. So we saw this. So in the case of pages that are containing code, that area that has code is mapped to a portion of the executable binary. Okay, and then the initial values of that area come from that executable binary file. Okay, so that's how we get data copied back and forth from executables into memory. The file can also be an anonymous file, meaning it's a file. It's some anonymous file that consists of all zeros. It's an anonymous file of arbitrary size that consists of all zeros. And so, of course, it doesn't exist. This is just a trick. So this allows us to create pages that are initialized to all zeros. Okay, and then so if a page is associated with the anonymous file, then the first fault will allocate a physical page of all zeros. So this is called a demand zero page. Okay, so it's brought in on demand, and then it's initialized to zeros. Once a page that's backed by an anonymous file is written to or dirtied, then it's like any other page. Okay, and then dirty pages are copied back and forth between memory and a special swap file. Now you remember, normally processes don't share anything with each other. Okay, but it's possible using this idea of mapping for processes to be mapped to the same objects. So suppose that we have two processes with their own separate virtual address spaces, and the pages in these two processes are being mapped to portions of physical memory. So let's say there's an area, a segment in process 1 that's been mapped to this object, so to this portion of a file. Okay. Now, process 2 can also map to that same object. And notice, even at a completely different virtual address. So there's no relationship between the region of this virtual address space that's mapped to the shared object in process 1 and the region of the virtual address space in process 2 that's mapped to the same object. And the kernel, because these objects have unique names, right? They're files. The kernel can check the other processes to see if any other processes are mapping to that object, and if so, map this region of the virtual address space to those same physical pages. Okay, so now we have a situation where each process is accessing some chunk of its virtual address space, and those accesses are actually being done on the same region of physical memory. So this might be useful. You might imagine, say these processes are servers. Say you've forked a bunch of copies of Apache. You might want to have some kind of shared cache, maybe a shared memory cache between those, all those different copies. So this would be, in this case, your cache would be a file on disk, and then as you access regions of that file, those pages get copied into physical memory. So that would allow you to have a shared cache in the memory across all those processes. Now, sometimes there's another objects can also be private, meaning they shouldn't be shared, okay, across processes. And there's an especially interesting kind of private object called the private copy on write object. So the idea here, and you'll see this will become very important when we look and see how fork actually works. The idea is that we have an object we have two processes that are mapping to the same object, but instead of this being a shared object, it's what we call this private copy on write object. And just like before, these two regions of the virtual address space map into the same region of physical memory, but they're tagged using and this is where those flag bits come in. The pages in this area are flagged as private copy on write. Okay, now what that means is, normally, if this was a shared object, let's say this was a shared object, and process 2 did a write into this region of the virtual address space. If this was a shared object, that write would also be reflected on the disk, on the file on disk. Okay. But if it's flagged as, instead of being shared, if that area, this area is flagged as private copy on write, then if process 2 does a write to a page in that area, then instead of reflecting that change in physical memory and on the shared object, it makes a copy of that page, a separate copy of that page, and maps it to some unused portion of the physical address space. Okay, so that's why we have the name copy on write. So if we read values from this area, nothing happens. It will just read from this portion of the physical address space. Okay, it's only when we do a write to some page in an area that's flagged as private copy on write, it's only when we do that write that the system first makes a copy of that page and then does the write. Okay. Now, why on earth would anybody want to do this? Actually, this notion of copy on write is another one of these kind of fundamental important system concepts that's used a lot whenever you want to share things efficiently. Yes?
Well, couldn't you have like two processes that want to write at the same time, and then you don't know like which one they're going to be writing to, essentially? Like, couldn't you get some issue if you didn't do this?
If you,
So, like,
well, the writes all go through. Yeah, the memory system. Okay, this is a really good question, and it's beyond our scope. But the memory system takes care of those And it provides some guarantees. So the memory system, you're right, it's receiving, from multiple cores, it's receiving multiple instructions, multiple addresses. And the memory system itself takes care of sort of providing some ordering on those. And it provides some sort of non-trivial guarantees on what you can assume the ordering is. But that's a pretty complicated topic that we won't get into. It's called the consistency model. So every processor provides some kind of consistency model. Any other questions? Okay, so why is this copy on write technique useful and interesting? Well, it turns out, I mean, if you think about fork, it seems like it would be terribly expensive, right? If you want to fork a process, you know, the naive way to do it would just be to you have to somehow get an exact copy of the address space, but a separate copy of the address space that's identical. So if you approach this naively, you'd have to make copies of all the page tables, all of the other data structures, and you'd also have to copy all the memory, right? So if you're forking a process that's created a huge number of virtual pages in its address space, those would all have to be copied to and mapped to different portions of the physical address of the memory. Okay, so it would be very expensive, right? Potentially almost unbounded, depending on how much memory you were using. Right, but fortunately, this copy on write technique provides an efficient solution. And so the idea, when we do fork, when a process executes fork, the kernel has to create exact copies of all those internal data structures, the struct, the area struct, and the page tables. There's no way to get around that. Okay, but those aren't really huge. They're not as potentially huge as the actual data that the program is accessing. And then it flags each page in both processes as read-only. Okay. Even though they're not, no matter where they are, any process, any page in that process, it flags as read-only. And then it flags each VM area struct in both processes as private copy on write. So on return, now each process has the identical address space because it has identical page tables. Okay, we've made copies of the page tables and all of the other structures. And as long as those processes just read, then they're sharing the same physical pages. Right? It's only when a process does a write that the system will create a new page, using this copy on write mechanism. So it's only when a process writes to a page it tries to do a write, the page is flagged as read-only, okay, in the PTE. That triggers a fault. The kernel looks at that, looks up the flags for that particular page, sees it as private copy on write, and so it makes a copy of the target page and maps it to a new region of the physical address space, and then and then when the write executes again, and then it restarts when that fault handler returns, it restarts that instruction, and now the write is writing to the copy. Okay, so what this does, a very clever technique, it defers the copying till as late as possible, and it only does copying when it's absolutely needed. Okay, so in some sense, it provides you with the most efficient way most space efficient way to represent those two different virtual address spaces. And so what's interesting is that regions of the virtual address space that are read from never get copied, right? So So it's perfectly fine for those two processes to share that data on physical memory because it's never written to, right? So, okay, so that's why fork isn't so bad, right? Now, execVE, now that we know about sharing or now that we know about this mapping notion, the execVE function loads and runs a new program in the current process. Okay, and so what it does is it frees all the area structs for the current process, right? So exec's not creating a new process; it's running a new program in a new virtual address space within the current process. Okay, so it frees all the area structs and page tables for the current process. Okay, and then it creates new area structs and page tables for the new areas. And the programs, so the program and initialized data, those areas are backed by the file, in this case the executable binary. And the program is backed by the portion of the executable that contains code. And the data segment is backed by the portion of the executable file that contains initialized data. So these two together are private, what we call they're private. Okay, this object isn't being shared with anything else. And it's file backed because this area is backed by portions of a file. The uninitialized data, which was specified in the BSS section of the binary, that's defined as a private demand zero area. Okay. So these pages will all be, remember by definition BSS is uninitialized. Okay, and so the system initializes these to 0. So any pages in the heap are also private demand 0. Now the memory mapped region for shared libraries, remember every process shares the same copy of libc in memory. So this is a region, the virtual address space, that's shared, okay, because it's shared by multiple processes, and it's backed by files of, and the file in this case is the .so file, the shared object file, and the code for this region is backed by text, the portion of this object file that contains code, and data initialized data is backed by a portion of this file that contains data. Now I haven't shown it here, but there's other portions of this region that need to be private copy on write because different libc functions, if a libc function has static variables or contains state, like a random number generator, typical random number generator retains state across each invocation. Okay, so that state would be different for each process. So there needs to be a sort of private copy on write area for any data that's being written to. And I suppose the system would just if you made this entire region no, you'd have to have second portions of this that would be private copy on write. And then the stack is private demand 0. Okay, so what exec does is it just sets, it creates new areas that are backed by the object file that you want to execute. And it creates areas for BSS and stack that are backed by anonymous files, and it creates this memory mapped region that's a shared object which corresponds to libc. And then it sets the program counter, RIP, to the entry point in text. And then as this program runs, now notice we haven't loaded anything, right? All we've done is set mappings. We've just created data structures in the kernel. And we've created mappings between portions of the address space and these objects. But nothing's actually been copied into memory yet. Okay, this is all we've just created. We've modified data structures in the kernel. Now, but once the loader sets RIP to the entry point, the first instruction in this text segment, then Linux will fault in all the code and data that's needed on demand. So loading is deferred until the loading of a page of code or data is deferred until that code or data page is actually referenced and accessed. So this is very clever and very interesting, I think, how it's like yet another example of how useful and tightly integrated virtual memory is with the operation of the system. Right? You wouldn't have to do this. You could just, as part of the loading process, you could just take those object files. You could just have a loop that would read these object files and just copy them into memory and create page table entries for them as you did it. But even that would be efficient. That would be inefficient too, right? What if you had a very large array that you had initialized to some non-zero value? That would require you to copy that entire array in at load time, even though you may be only accessing a small portion of that data structure. Now, the kernel provides a function called mmap that allows you to do your memory mapping just like the kernel does. Okay, and so it's basically it's a system call that allows you to request the kernel to map a region of virtual memory on its behalf. And so this mmap function takes a pointer, which is some pointer into the virtual address space, and it tries to map length bytes starting at this address. It tries to map that portion of the virtual address space to the object, to an offset, to some object specified by this file descriptor. Okay. So remember, when you open a file, you get back a file descriptor. So it's mapping this region of the virtual address space, starting at start for length bytes, to a region of the file denoted by this integer file descriptor. So it's mapping length bytes in that file starting at offset. Now, and then there's the user can specify different flags, what kind of protection they want for this whether it's private or whether it's read or whether it's read only or read write. And they can also specify the type of object. If you map an anonymous, if you use this flag in mmap, then you get a demand 0 page. Okay, that's the anonymous file. In which case you don't need to specify this file descriptor. And you can map that object as being private or shared. Okay, like we talked about before. Now the kernel will return a pointer to the start of this mapped area. Not necessarily, this start address is like a hint to the kernel. So if it can, it will try to map that area. But if that portion of the virtual address space is already contained in some already existing area, then it'll pick an unused portion of the virtual address space to map. Okay, so what we're doing really is we're taking an offset into some file specified by that FD argument and length number of bytes, and we're associating that or mapping that into the same sized region of the virtual address space. Okay. So now if we read, now again, nothing gets copied. Okay, it's just a mapping. So that if we were to read a portion of, let's say we mapped an unused portion of the virtual address space, and then using mmap. And then after mmap, we just started scanning through this portion of the virtual address space. You know, say it's an array. We've mmapped a big array. As we read, each non-existing page will be swapped in automatically. Okay, it'll trigger a page fault, and it'll be swapped in, and the value that it has will be determined by the contents of this portion of the file. Okay, and then, so here's an example of how we can use mmap to do, and this is kind of an interesting example. We're copying a file from standard in to standard out without ever transferring data to user space. So the normal, the sort of naive way to do this would be to read from a file, read from standard in, and then write to standard out. So 2 syscalls, one read and one write. We can actually do this using one mmap and then a single write. Okay. So what we do is we open a file. argv1 is standard in. I'm sorry, we open a file that was passed in on the command line. We get its size, and then we call this mmap copy function to say copy the bytes, the size bytes from this file to standard out. So this mmap copy function does mmap using that file descriptor, sets it as read-only, private, sets the size, and length means everything, or at an offset of 0. And then we do one write syscall to standard out, passing it the pointer to the buffer that we want to copy and of size bytes. So this will read bytes one after the write call will read bytes in buff P one after the other, and as that happens, they'll be faulted in, and then it will write them. It will write them to the descriptor indicated by the 1, which is standard out. Okay, so that's it for today. Hope you guys have a good weekend, and see you next week.